Hello my dear students. So in my previous class we started understanding about the remaining part of electrochemistry. So there we started with E.M.F of a cell. So that is electromotive force, what is meant by electromotive force. Then the theory of Daniell cell and Nernst equation for the reduction potential of an electrode. And what are the electrochemical conventions we are going to use in the study of electrochemistry? And according to the IUPAC convention, how the potential of standard hydrogen electrode is considered, and what is oxidation electrode, and how we are going to represent a cell and E.M.F of a cell, how we are going to calculate the E.M.F of a cell. So that is E.M.F is given by the relation, that is E cell, that means E.M.F of a cell is equals to the reduction potential of the right hand side electrode minus the reduction potential of the left hand side electrode. And further we deduced a Nernst equation for E.M.F of a cell, and at last in the end of the session we discussed or understood about liquid junction potential. So that is the potential which develops at the junction of the two liquids. So why does this arises? So this is because if a cell is formed by combining two electrodes which contains either different electrolytes or same electrolyte but with different concentrations, so we are going to observe a potential difference, that too especially at the junction of the two electrodes. So that is what is called as a liquid junction potential, and this potential arises due to the diffusion of ions from a region of higher concentration to a region of lower concentration across the boundary. And how we are going to minimize this liquid junction potential, that is by using a salt bridge or connecting the two electrodes with the help of a salt bridge which contains a salt with the ions having same velocities, so we can reduce the potential of this junction. And next we also learnt how to prepare this salt bridge, right? So this is where we stopped in our previous class, and in this session, so let us move further and understand what is meant by electrochemical series. So a series of electrode systems obtained by arranging them in the increasing order of reduction potential is called as electrochemical series. So some of the electrode systems of the series are listed here. So that is, if we construct an electrode with the lithium, so then the reduction potential in volts will be equal to minus 3.04. So these are the reduction potential in volts which are already founded out or experimentally examined and finalized. So what exactly is the electrochemical series? Electrochemical series, also sometimes it is referred to as activity series, is a list that describes the arrangement of elements in order of their increasing electrode potential values. The series has been established by measuring the potential of various electrodes versus standard hydrogen electrode. In electrochemical series, the electrodes, that is either metals or non-metals, so these electrodes will be in contact with their ions and are arranged on the basis of the values of their standard reduction or oxidation potentials. Standard electrode potential is obtained by measuring the voltage when the half cell is connected to the standard hydrogen electrode under standard conditions. So the electrochemical series is a simple way of visualizing similar versus dissimilar metals. For roofers, you need to know what compatibility issues exist in regard to material. So this is a chart which I am showing here. So this chart is a common roofing metals which are shown, and in most basic terms, metals that exist further apart from each other on this scale will react with a higher propensity for corrosion than ones that are close together. That is, so zinc and copper, which is equals to far apart on the scale. If you observe zinc and copper here, so they are far apart in the scale. This means that so you would never have a copper pipe draining water onto a zinc coated roof. So these are some of the basics of electrochemical series. And if you observe in this electrochemical series, in this chart what I am showing here, so lithium is at the top of the list. So this is lithium, so this is at the top of the list, and fluorine is at the bottom. The magnitude of the potential is a measure of the ease to reduction reaction to occur at the cathode. Thus, copper is more easily reduced than zinc. So this is what just now I explained, that is zinc and copper, they are far apart on the scale. So the reason behind this is so copper is more easily reduced than zinc. So now let us move on to the applications of electrochemical series. So there are many applications we are going to see by using this electrochemical series. So some of them are oxidizing and reducing strength. With the help of this electrochemical series, we can understand the oxidizing and reducing strengths. And also for the calculation of standard E.M.F of our electrochemical cell, we need this electrochemical series. And for the predicting the feasibility of redox reactions and predicting the product of electrolysis. So these are some of the very important applications of this electrochemical series. So let us understand one by one. So the first one is calculation of E.M.F of a cell. So as we have already discussed or learnt, the E.M.F of a cell is given by the relation. So E cell is equals to reduction potential of the right hand side electrode minus reduction potential of the left hand side electrode. Since the values of reduction potentials are available from the electrochemical series, we can calculate the E.M.F of the cell theoretically. So if one value is known, definitely the other value could be easily found out. So let us take an example. So to calculate the E.M.F of the cell Zn Zn2 plus Ag plus Ag. So here, so we know, so we have to calculate the E.M.F of a cell. So that is E naught cell. So which is equals to 0.8 minus 0.76. Okay, so this value I got it in the electrochemical series. You can go back and check it here. So the reduction potential for zinc, so if you see here, the reduction potential for zinc is minus 76. Okay, so that minus 76 I have used, and the reduction potential of silver is 0.80. so that is what the values I have taken here. 0.8 is the reduction potential of silver, and minus 0.76 is the reduction potential of zinc. Substitute these two values, so we are going to get 0.8 plus 0.76, which is equals to 1.56 volts. So 1.56 volts is the E.M.F of a cell which is given here, that is Zn2 plus Ag plus Ag cell. And the next application is to determine the feasibility of a reaction, as I said. So consider this cell, experimental cell or electrochemical cell. So here let M1 plus N be the oxidation electrode and M2 plus M2 be the reduction electrode. The E.M.F of the cell is calculated from the electrochemical series if the calculated value of the E.M.F for the cell is positive. Then the cell reaction is taken as it is feasible. And the third application is to determine or the determination of Gibbs free energy, that is delta G naught, and the equilibrium constant K of a cell reaction. When an electrochemical cell operates spontaneously and reversibly, so the electrical work done will be represented as W max is equals to minus N F E naught, where N is the number of the electrons transferred and F is the Faraday, so that is 96,500 coulombs, and E naught is the E.M.F of the cell. So this is work done at the expense of free energy of the system. Let delta G naught be the free energy change. So here delta G naught is the free energy change. So then what happens to this expression? So delta G naught is taken to the left hand side, and delta G naught will be equals to minus N F E naught. So let me call this equation as equation number 2. Knowing E naught, so that is the E.M.F of a cell, and delta G naught can be calculated, that is free energy change can be calculated. So therefore, so delta G naught will be equal to minus RT ln K. So this is when free energy change and equilibrium constants are related, so we can represent it as delta G naught, which is equals to minus RT ln K, and let me call this equation as equation number 3. From equation 2 and 3, so observe this equation 2 and 3. So I can write it as minus NF E naught is equals to minus RT ln K. Okay, so this is because so here if you observe these equation number 2 and 3, so both are the definition of change in free energy, that is delta G naught. So that is why so minus NF E naught can be written as minus RT ln K. So now rearranging this equation, so I am going to get, so if I take ln K towards the left hand side, so ln K will be equal to NF E naught divided by RT, or converting it into its logarithmic form, log K is equals to NF E naught divided by 2.303 RT, or if I retain only K towards the left hand side, that is equilibrium constant. K is nothing but equilibrium constant. So suppose if I have to determine the equilibrium constant, then I have to retain K in the left hand side. So then K is equals to anti-log NF E naught divided by 2.303 RT. So hence the value of K is obtained from E.M.F measurements. So let us consider an example to understand how we are going to determine the free energy and also as well as equilibrium constant. For an electrochemical cell, that is the same cell I have considered here, Zn2 plus Cu2 plus Cu, the equilibrium reaction is written as Zn plus Cu2 plus so which is a reversible reaction, so that is why it is called as an equilibrium reaction. It can, when the reaction is reversible, definitely it can reach a state where we call it as a equilibrium state. So the equilibrium reaction is represented in this way. Under standard conditions, substitute all the values whatever is known. So here R is constant, that is universal gas constant, and temperature, suppose if we consider 25 degrees centigrade, so then it can be it is represented as 298 Kelvin, and here N will be equal to 2. Okay, so N is equals to 2, and F is 96,500 into 1.1. So we are going to get 1.61 into 10 raised to 37. So this is the equilibrium constant of this particular electrochemical cell. And the next application is prediction of displacement reaction. Any metal will reduce any cation found in the series. For example, when zinc metal is added to copper sulfate solution, copper is displaced from its salt solution. So in solution, zinc undergoes oxidation. So this is the oxidation reaction. So the zinc is going to lose the electrons to electrons, that means it is going to get oxidized to form Zn2 plus. The electrons generated reduce Cu2 plus ions present in the solution to Cu, that is copper. Cupric is going to get reduced to copper. So the copper deposits on zinc, and this is the reduction reaction which is going to take place. So in the same way, we can also give another example where the standard electrode potential of zinc and nickel are found to be minus 0.763 volts and minus 0.25 volts respectively. So this you can go back to the electrochemical series and check the standard electrode potential of zinc and nickel. So from the electrode potential values, it is clear that when zinc or nickel electrodes are separately connected to standard hydrogen electrode, both will have negative polarity and both will act as oxidation electrodes. That means oxidation electrodes are nothing but anodes. If they are manually connected, then zinc will be the oxidation electrode and nickel will be the reduction electrode. So the overall cell reaction, so what happens? So in one, so the reduction is going to take place, and in nickel, the reduction electrode which has been connected, so the nickel is going to get reduced. So here zinc is the reducing agent and it reduces nickel ions, that is Ni2 plus ions to Ni. At the same time, so Ni2 plus ion is a strong oxidizing agent and it oxidizes Zn, that is zinc, Zn2 plus. And the overall E.M.F of the cell also can be calculated like E cell, that is E.M.F of the cell, which is equals to E.M.F of nickel minus E.M.F of zinc. So these are the four important applications of electrochemical series. So next is, let us move on to how to measure the E.M.F of a cell. So this is a schematic representation of experimental setup. So how we are going to construct this experimental setup is, to the end A, so if you observe here A, so to this end, so just like how we have calculated or how we founded or measured the resistance, okay, so how we measured the resistance, in the same way with the slight modifications we have made connections here. So in this so A, we have connected a potentiometer, so this is a potentiometer, and the positive of an accumulator is connected to this. The negative terminal is connected to the B through a plug key. Okay, so this is a plug key and this is a negative connector which has been connected to the end B, and this forms the primary circuit. In the secondary circuit, so the positive terminal of Wesson cadmium cell is connected to A end. The negative terminal is connected to the sliding contact through a galvanometer. So this is a galvanometer. And the accumulator and the standard cell are introduced into the circuit. And here the sliding contact, so this is the sliding contact and this is moved so as to obtain the balance point D1. Okay, so this is D1. So this is D which has been situated in between A and B, and here a sliding contact also will be located or inserted, and this sliding contact is moved so as to obtain the balance point D1. At the balance point, the deflection in the galvanometer is 0. So here, so this is the balance point, and here, so the deflection in the galvanometer will be observed as 0. Length AD1, so the length, that is the distance between AD1 is noted. The standard cell is disconnected and the experimental cell is introduced, and the balance point D2, that is AD2, is noted or obtained. The length AD2 is noted and E.M.F of the experimental cell is then calculated. So this is the calculation part. So where the E.M.F of standard cell is given, so E.M.F of standard cell will be the known value, so it is 1.0186 volts, and balancing length for the standard cell, that is AD1, will be proportional to the standard EMF of the cell. So the EMF of the standard cell is known, that is 1.0186. So that is why, so the balancing length for standard cell, that is AD1, is proportional to 1.0186 volts. Balancing length for experimental cell. So this is for standard cell, and in the same way, so the balancing length for experimental cell will be equal to, or it is expressed as AD2 is proportional to the E.M.F of the experimental cell. Therefore, with the help of these two values, the E.M.F of experimental cell is represented as 1.0186 into AD2 divided by AD1. So this is how we are going to calculate the E.M.F of a cell. And next is types of electrodes. Many types of electrode system are used in E.M.F measurement. They are primary electrode, and it is also called a standard hydrogen electrode or gas electrode. And the second is a secondary electrode, and there are two different types in secondary electrodes. So one is reference electrodes, for example calomel electrode or silver chloride electrode, and oxidation reduction electrodes, for example quinhydron electrode or ferrous electrode, that is iron electrode. So these are the different types of electrodes which we are going to use. So I am going to stop it here, and in my next class we will understand how to construct a standard hydrogen electrode and how the working of this standard hydrogen electrode is understood or carried out. So thank you, dear students.